Okay, so now you can see my screen. So today is the third interactive session, and as per your week three, for week three, the topics covered were in week one we did classification, in week two we did soil volume relationships, weight volume relationships, and then in week two we had also studied permeability and seepage, which we did not cover last week. So in week three, you have studied again a portion of permeability and seepage and compaction. Mainly, we will try to cover permeability and seepage today, and if some time is left, maybe we can start compaction. Otherwise, next week we will have a dedicated session for compaction. Okay, so let's move on. First, we can do one thing. We can discuss what is it that we studied in permeability. So there are two concepts, permeability and seepage. So permeability just means that if you have a soil body based on the pore structure of this soil body, what will be the rate of flow of water through this soil body based on the pore structure. And coarse grained soils have uh, higher diameter pores, so they are freely draining. The water does not encounter resistance in case of coarse grained soils, gravels, and sands. However, in fine grained soils, the pores are so small, the diameter is so low that you encounter capillary forces. When your diameter is too low, you will the downward gravity force will be almost equal to, like, it will be countered by the upward capillary force which takes place due to, see, if I take a thick tube and I have a column of water that wants to pass here, so there is a force, we can say, of adhesion, this surface tension, a force that will resist around this tube, and a force that is going downwards. The force going downwards is the weight of this column. Now, when the diameter is too large, what happens is that this weight is much, much greater than this resisting force. Much, much greater than. It's not even comparable. That is why what happens is that we say that we have encountered negligible friction, negligible resistance to flow. It's not negligible, like there is resistance to flow based on the diameter, but the difference between coarse grained and fine grained soil is that when the diameter is low, the weight of this column reduces such that this is now comparable to these forces. That is why here we encounter more resistance. So when we talk about soils, we firstly classify coarse grained and fine grained. Then we talk about, because they have totally different behavior, we talk about how fine grained behave with water and coarse grained behave with water. So in permeability, you have studied the Darcy's law which states that if you have a column of soil, this is basically kind of an energy conservation. We know that just like water flows from a level, higher level to lower level, there is high potential here, low potential here, water will flow here. You know, heat will flow from higher temperature to lower temperature, high potential to low potential. Same is the case with soil. Here, you have a gradient. So, high potential here, low potential here. If you have high uh, head here, low head here, the water will flow in this direction. So that is now Darcy's law states that V is directly proportional to I, which means that the velocity of the water, the velocity with which this water will move, is directly proportional to the hydraulic gradient. Greater the gradient, greater will be the flow of water. Greater the gradient, greater will be the flow of water, and this is a kind of fundamental property of soil based on its structure. If we talk about it, based on its structure and pore space, it will have a particular resistance to the flow that contributes to this proportionality constant, which is V is equal to K I. Now you have a hydraulic conductivity and you have an intrinsic permeability. Intrinsic permeability is only due to, sorry, only due to the pore structure, while the hydraulic conductivity also accounts for the viscosity of the fluid flowing, the temperature at which the fluid is flowing, because these, the viscosity, the temperature, they inherently affect the properties of the fluid which is flowing. For example, if instead of water, oil is flowing here, it will not move with same speed as water. But when we talk only and only about soil structure, which is intrinsic permeability, then we say that it is a fundamental property because it's based on only the pore structure. So in permeability, uh, we studied how what permeability is. Then we studied how we calculate permeability. So there are some tests in lab. Now, because coarse grain soils are freely draining, fine grain soils are not so freely draining. So we have different tests for different soils. So we have a constant head permeability test in lab for coarse grain soils. Then we have a falling head permeability test for fine grain soils. I'm sure you studied this. I will not go in detail with this. Then you have some field tests, how we conduct permeability in a field. Why is it necessary to conduct permeability in a field? Just as I said that you are talking about pore structure, isn't it? Now, if you take a sample from a ground and this is a disturbed sample, you collect only this part and it gets disturbed. Somewhat, it gets a little squished or expanded. So will this reflect the actual permeability in field? Also, because the soil is heterogeneous, the permeability reflected here will not be equal to the permeability reflected here. That is why we conduct field tests in which we calculate the permeability in field without the requirement of taking the sample, because the disturbance to the sample can give us very different values for permeability. Okay, so that is that. Then we talk in permeability. Then we talk about stratified deposits. If you have a sand, then you have clay, and then you have something else. How will the water behave in this scenario? If the water is flowing in this direction, if the water is flowing in this direction, how will this behave? So that was basically what you studied in permeability, and then you talk about seepage. Now, how is seepage different than permeability? Seepage is different because in seepage, water is flowing through the soil. In permeability, we are just trying to determine that if the water will flow, uh, how easily will it pass. In seepage, the water is already flowing. Okay. Now we are trying to see that due to this flow of this water, like how much force, for example, is getting generated by this flow of water. So that is what we study in seepage. So let's move on and try to solve some questions. Do you have any question? Okay, okay. So let's move on to the first question. Results of constant head permeability test for a fine sand sample have a diameter of 150, having a diameter of 150 mm. So, and then for what kind of soils do we perform constant head permeability test? No, no, not the samples. What kind of soil, fine grained or coarse grained? Why do we perform falling head for coarse grained? See, what happens in lab is you have this mold, okay, and this is filled with soil. Then you take a standpipe. I'll show it here. In lab, you have this mold. You take a standpipe and you take a ruler here. Okay. There are two ways in which you can calculate. What we want to know is how much water. One second. Sorry for my drawing. And we have a ruler here. What we can do is this standpipe. Excuse me. Let me actually make this easier. Okay. So we have a standpipe, we have a mold, and we have a ruler. Let's say that this is a ruler. Okay. So I pour some water in this pipe. I pour some water in this pipe, and with time the water will flow. And what I will do is from this ruler I will calculate I will time from this height to this height, how much time did it take? Okay, so I know L1, I know T1, I know the area, so I know the volume. So I know in volume 1, for volume 1, T1 time was taken. I know how much water discharge is taking place here, isn't it? Now, in fine grained soils, because the permeability is very low, this will take almost this will take at least a minute to come from here to here. So I can calculate like T1 will be like 5 seconds, 12 seconds, or something like that. But in coarse grained soils, the flow of water is so high that as soon as you put some water here, it will gush down. You will not get any time to record any T. So instead of calculating the discharge from here, what we do is we take a measuring flask at the end, okay, and say for time T1 I have fixed in 10 seconds. I check how much water did flow through the soil sample. So the main thing is the practicality, because in falling head the rate of flow will be so low, like in fine grained soil rate of flow will be so low, so this will become impractical. In that case we will fill the standpipe and we'll check on this ruler how much time did it take for water to flow from x1 position to x2 position in fine grained soils, because permeability is low. In coarse grained soils, because the speed of the water is so high, we what we do is we collect this water and check in intervals of time how much volume was collected. But you must know that from here also we are calculating the volume of water. From here also we are calculating the volume of water per time, per unit time, per unit time. So basically, for both the tests, we are calculating the discharge. Okay, so let's move on. Let's try to solve this question. Do you have any question, Anand? Okay. Has anybody else joined the class? Okay, the results of a constant head permeability test for a fine sand sample having a diameter of 150 mm and length of 300 mm are as follows. The constant head difference is 500 mm. The time of collection of water. The constant head difference means now, see, as I said that we are collecting water in the bottom, isn't it? But but as we pour, everything is going out, everything is going out, everything is going out. So first we need to uh, first we need to establish a steady state, because Darcy's law is valid for steady state only. Okay, so what we do is we take a container here, okay, and we put water in this at, for example, Q1 discharge. We just a pipe. Now the flow of water through this pipe should be such that the level of water in this overhead container should remain constant. And how will it remain constant? That Q1, the water that we are putting in, if it is equal to Q2, if Q1 is equal to Q2, what will happen? The amount of water leaving is equal to amount of water entering. So this level will not change. This will remain constant. So we need to change the discharge of our incoming water to such that we reach a state where this level remains constant. Now, for example, I have an overhead container here at height h. We have established a constant head, which means that I am pouring in water from here such that this level is not changing, and then water is going into the soil, and then it is coming out of the soil, and this is the head it is talking about, the constant head. Constant head difference is 500 mm. This is 500 mm. Time of collection of water is 5 minutes. So the beaker I took here, the measuring flask I took here, I collected water in it for 5 minutes. Volume of water collected is 350 centimeters, and in 5 minutes I collected 350 centimeter cube. Okay, and the temperature of water is 24 degrees Celsius. Okay, and now we have to determine the hydraulic conductivity of the soil at 20 degrees Celsius. First, let us talk about the permeability. Did you understand the question? Can you solve this question? Can you try? We know that V is equivalent to K I, isn't it? And velocity we can write as discharge by time, isn't it? Velocity is uh, discharge by area. Discharge by area, isn't it? And discharge is basically volume by time. So volume by area into time is our velocity. You study this in fluid mechanics. Now you have K and I. You know what is hydraulic gradient? It is the what is hydraulic gradient? It is the head available per unit length which the water has to travel. I is equivalent to H by L. So if I put it here, I will have V by A into T equals K into H over L. And K will be equivalent to V L by A H T. So we know the volume that was collected. So our permeability will be, the volume collected was 350 centimeter cube. The length of the sample is 300 mm, which means 30 centimeter. Okay, divided by the area of flow is, this is 150 mm diameter, pi by 4 into 1.15 square, and then we have T is 5 minutes, so we can write 5 in 5 into 60 seconds, and we have H is given as 500 mm, which is 50 centimeter. Okay, let's calculate this quantity. So this comes out to be K equals 3.96 into 10 to power minus 3 centimeter per second. Now the question is that the temperature of water is 4 degrees, 24 degrees Celsius, but we have to calculate the hydraulic conductivity of soil at 20 degrees Celsius. So basically, the conductivity uh, at the permeability at T degrees Celsius and permeability like T1, T2 is directly proportional, is inversely proportional to the viscosity of the fluid. This is very easy to understand. Thicker the fluid, lower the permeability. Thinner the fluid, higher the permeability. So we can write that KT1 mu1 equals KT2 mu2, and we know at T1 is, let T1 be 20 and T2 be 24. So K20 mu 20 equals K24 mu 24, and we want this. So K20 equals K24 into mu 24 over mu 20. So viscosity of water at 24 degrees Celsius and viscosity of water at 20 degrees Celsius. So we can check this from a table. This was just the purpose of this introducing this was just to make you understand that how the permeability will change with temperature. So I will give you the value of this quantity. It is equivalent to 0.91. So you can write that K at 20 is 0.91 times K at 24, which is 0.91 times 3.96 into 10 to the power minus 3 centimeter per second, which will be equal to 3.6 into 10 to the power minus 3 centimeter per second. Now let us move on to the next question. So the next question is, for a falling head permeability test, the following are given. The length of specimen is 15 inch. The area of specimen, sorry, I do it in a line down. Let's draw it like this. Length is 15 inch. Area is 3 inch square, and the permeability given is 0.688 inch per minute. What should be the area of the standpipe? As I said that in falling head permeability test, we take this standpipe What should be the area of the standpipe for the head to drop from 25 to 12 inch? And I also said that we have a ruler there. So it's saying that the head is dropping from 25 to 12 inch, which means the length of fall is 25 minus 12, which is 13 inch. And the time in which this fall takes place is 8 minutes. Okay, so I have to calculate the area of this standpipe such that these. So basically, what am I doing? I'm calculating the volume of water that is flowing through this. I know the length, I know the time. So how I will calculate the volume? We'll multiply the length by area, isn't it? You know, in falling head permeability test, you derive this formula 2.303 AL by 80 log to the base 10 H1 over H2, isn't it? So, Anand, can you calculate this for me? You have AL over 80 log to the base 10 H1 over H2. Okay, can you calculate this for me? Let's take a break for 5 minutes. Okay, I'll take a break for 5 minutes. I'll be back at 6:45 sharp. And if you can calculate the answer for this till then, that would be nice. Okay, Anand. Did you get the answer? Okay, no issue, no issue, no issue at all. Okay, so what's my pointer? This will be 2.303 times, we have to calculate A, into L is the length of this sample, which is 15 inch, over capital A is the area of this sample, which is given as 3 inch square, into time is 8 minutes. We will write 8 into 60. Okay. No, we don't have to write in seconds because the permeability is given in minute. Let's write in minutes only. 3 into 8 log to the base 10. H1 is 25 and H2 is 12. Now this is equal to, it has already been given, 0.0688. So the area of the standpipe should be equal to 0.0688 multiplied by 3 into 8 divided by 2.303 into 15 into log to the base 10, 25 over 12. Okay, this comes out to be, let me check, this comes out to be 0.15 inch square. So this is the area of the standpipe in the experiment, such that the dimensions of the uh, soil sample are 15-inch long and with an area of 3-inch square, and the water is flowing, the soil has a permeability. This water is flowing 13 inch in 8 minutes. Okay, so this is the area of the standpipe. Okay, let's move on to the next question. A permeable soil layer is underlain by a, an impervious layer as shown in figure here, with K equals 5.3 into 10 to the power minus 5 meter per second for the permeable layer. Calculate the rate of seepage through it in meter cube per hour per minute. If the width, if H is 3 meter and alpha is 8 degrees. So what is the significance of the impermeable layer here? The significance of the impermeable layer is that the water is flowing in this direction and no water will cross here. No water will cross here. Water is only flowing in this direction. And what is the significance of this tilt? You know that if the water was, if there was no tilt and then there was no pressure from here, the water would not move. Just like in a bucket, if you fill two buckets, you connect them and they have same level, the water will not move unless and until there is a head difference. This creates a head difference and a hydraulic gradient in the soil. So because this is permeable soil, water will flow in this. This is impermeable, so there will be no cross flow through this impermeable layer. So we have to calculate the rate of seepage. As I said, that the water is already flowing. We have to calculate at what rate this water flowing. The rate will depend upon the head difference. It will depend on the permeability. How easily the water can pass and how much is the gradient, how much is the head difference that the water feels the need to stabilize itself and reach an equilibrium. Okay, so let's do that. First of all, what is the length of the flow? Calculate the hydraulic gradient. We need to calculate hydraulic gradient is the head difference over the length of the flow. Sorry. Okay. So if we know this, H is equal to 3 meter, and this will be the length of the flow. Okay. So let's first calculate this perpendicular distance. Okay. So since this is alpha, how much will this be? I have a triangle. This is 90. This is 90 minus alpha, and this is 180 minus 90 minus alpha. So this angle here is 90 plus alpha. This angle is 90 plus alpha, and if I want to calculate if I drop a perpendicular here, which means this will be 90 and this will be alpha, isn't it? So I have a triangle here in which this is 90 and this is alpha, this is h. So from trigonometry, this is the base cos alpha will be this, let's say this is H over H. So our H equals H cos alpha, this perpendicular distance. Are you following me, Anand? Okay, so this is alpha. Let me actually draw a line because this is getting very shabby and I'm not able to. Um, okay, so this becomes alpha and this becomes H cos alpha. Now, what will be this distance? If we take this uh, triangle, again we will say if this is the length L and say this is S cos alpha equals S by L. L will be S by cos alpha. So our length is S by cos alpha. Okay. So how much is the head difference here? If we have this line here along the gravity, again we will have alpha here, isn't it? And this is S. So this distance will be, we want this distance. If we say tan alpha equals, this is delta H, which is the head. Delta H over S. So we will say delta H, the head difference is S tan alpha. This is equivalent to S tan alpha. So we know the head difference now. We know this delta H. Hydraulic gradient is S tan alpha. Oh, let me rub off the unnecessary parts. Now, the hydraulic gradient is delta H by L, which is S tan alpha over L is S over cos alpha. So our delta H by L will be equivalent to tan alpha cos alpha. We can write this as sin alpha over cos alpha into cos alpha equal to sin alpha. This is our I. So I equals sin alpha. Now we need to calculate the seepage. How much is seepage? Seepage is basically the volume of flow through a soil. Q equals K I A. We know the K 5.3 into 10 to the power minus 5. We know the I into sin alpha, and let us assume that in this direction this is 1. So the area of flow is H into 1, but the flow is taking place this way. So it's basically H cos alpha into 1. Flow is taking place like this. The area is H cos alpha into 1. Okay. So our Q will be equal to, let's calculate. This will be 5.3 into 10 to the power minus 5. We have to calculate in meter cube. Everything is in meter, that is fine. But here we have been given in seconds. Let's change this to hour. Over 1 hour is equivalent to 1 into 60 into 60 seconds. 1 hour is equivalent to 3600 seconds. So 1 second is equivalent to 1 by 3600 hours. So I divide 1 by 3600 into sine 8 into H is 3 into cos 8. Okay, so let's calculate. So this comes out to be 0.0789 meter cube per hour per meter. Okay, per meter means 1 meter in this direction. If we had been given like a column of width x meter, then we would just simply take the area as h cos alpha into x. But right now, because we have taken 1 meter in this direction, that is why we are adding this per meter. Okay, any question? Any question? Okay, so let's move on to the next question. So what have we been given here? Find the flow rate. Again, same thing, seepage or flow rate in meter cube per second per meter, which means 1 meter in this direction. At right angles to the cross section shown through the permeable soil layer shown in figure, given H is 8 meters, H1 is 3 meters, small h is 4 meters, S is 50 meters, alpha is 8 degrees, K is this much. So we need to find the Q. So here, if you see, these are impervious. The only pervious layer is the middle one. And since this is the direction of flow, we have to take from here to here only. We will take a perpendicular here, we will take a perpendicular here. And we saw that this perpendicular equals h1 cos alpha. So this is h1 cos alpha. Since this is s, we in previous question saw that this length will be s by cos alpha. In this, we just have been given h, we don't have to calculate this. So Q equals KIA is equivalent to K delta H over L over area. This is equivalent to 0.08 into delta H has been given 4 meters. Length we calculated S over cos alpha. S is 50 meters. 50 into cos 8. Then we have A. A is this h1 cos alpha. H1 is 3 meters. 3 into cos 8 multiplied by 1 in this direction. Okay. So this comes out to be 0.19 into 10 to the power minus 3 meter cube per second per meter. This will be our rate of flow. Okay. Any question? Okay. So let's move on to our next question. So we did a question on falling head, we did a question on constant head, we did a question on seepage rate. Now let us do a question on permeability of stratified soils. Okay. So we have been given a stratified soil deposit in which H1 is 1 meter, this is 5 meter, 1.5 meter. There is a correction here. This is 1.5 meter, this is 2 meter, and then K1 is 10 to power 4, K2 is 3.2 into 10 to power minus 2, and K3 is 4.1 into 10 to power minus 5 centimeter per second, centimeter per second, centimeter per second. Estimate the ratio of equivalent hydraulic conductivity. So when the water is flowing in this direction, it will flow it with a fast rate here because conductivity is high, then slower, then slower. So equivalent of, as in hydraulic conductivity, such that it was only one deposit. It was not a stratified deposit. That will be the equivalent hydraulic conductivity. So let's calculate that. Excuse me for a moment. So if we talk about equivalent hydraulic conductivity, what will be the velocity of flow in this? Velocity is equivalent to Ki, isn't it? Uh, See, if you see here, each have different delta H. They have different delta L. So the hydraulic conductivity, so the hydraulic gradient is not equal. But we say Q is equal to KIA. A is same for all. So Q1 is equal to K1 I1 A1, Q2 is equal to K2 I2 A, Q3 equals A3 I3 A. Okay, so equivalent will be kind of an average. The flow, for example, this is L1, sorry, H1, H2, H3. Our equivalent conductivity will be, the water is flowing with the conductivity of KH1 to H1 plus KH2 through H2 plus KH3 through H3 divided by the total length that the water is traveling through. This will be our equivalent hydraulic conductivity. So this will be 10 to power 4 into 1 plus 3.2 into 10 to power minus 2 into 1.5 plus 4.1 into 10 to the power minus 5 into 2 over 1 plus 1.5 plus 2. So let's calculate this. This comes out to be 107.07 into 10 to power minus 4 centimeter per second. But I made a mistake here. This was in the horizontal direction. We are multiplying. This is for the horizontal K equivalent. So the water is flowing through K1 in an area with an area of 1 meter into 1 meter. Then through K2 with an area of 1.5 meter into 1 meter. Then K3 with an area of 1 meter into 2 meter. And then the average height of flow is like we average it by the total height of flow. So this is the K equivalent in the in the horizontal direction. Now if you talk about K equivalent in the vertical direction, that will be different. For that, we will take H1 by K equivalent KV1 plus H2 by KV2 plus H3 by KV3. Okay, because here your area is same, but your Q is equivalent to KIA. Area is same, so Q1 by K1 equals A, Q2 by K2 equals A, and from there we take an average. This will be 1 plus 1.5 plus 2 over 1 over 10 to power minus 4 plus 1.5 over 3.2 into 10 to power minus 2 plus 2 over 4.1 into 10 to power minus 5. The mistake is that this is minus 4. Okay, and K equivalent in the vertical direction comes out to be 0.765 into 10 to power minus 4 centimeter per second, and this is K equivalent in the horizontal direction. Then we calculate the total equivalent hydraulic conductivity as K equivalent in horizontal over K equivalent in vertical, which is 107.7 10 to power minus 4 over 0.765 into 10 to power minus 4. This comes out to be about 140 equivalent hydraulic conductivity, K hydraulic. So this is what we utilize in our flow net when we have anisotropic soils that have different hydraulic conductivity in a vertical direction and different hydraulic conductivity in a horizontal direction. Then we take this. Okay. So let's take a break till 7:30, 7:21. Okay, 7:25. Let's reassemble at 7:25. 7:25. Okay, is that okay? Okay, let's reassemble at 7:25. अमर, 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 कौन भी फ्लाम, कौन भी फ्लाम। दर्द दर्द मुझे हर बार होता है इस मीटिंग, मीटिंग से हर बार होता है मुझे, मीटिंग से हर बार होता है, मीटिंग से ये क्लास से। Okay, so let's move on. Actually, those were the questions that I had prepared for this lecture. But since we have more time, let's move on and do some more questions. So, we have been given this diagram of a confined aquifer, and the question says that a pumping test. Uh, are you back, Anand? Okay, okay. A pumping test from a confined aquifer yielded the following results. So, you see where what we are doing here is this is the piezometric level before pumping, and then we are pumping out water from this well, and then we are checking this. Uh, this was piezometric level before pumping, and then we have at different times how the level in these wells will decrease. See, we are pumping out from here. Okay, we're not pumping out from here. So this is the well that we are pumping out from. Initially, all these wells had this water level. Now we are pumping out from here, not from here. But what will happen is that the head difference a head difference will be generated between these three wells. Okay, the water will have a tendency to flow into this well such that a new equilibrium state is developed, and all the wells are at the same level. So at t is equal to infinity, we will have this as the final level. Okay, but as soon as we will stop pumping, the head will increase again because that was the original equilibrium. Right now we are disturbing the equilibrium by providing a force of pumping. Excuse me, just a moment. Amar. Okay, so now Q is the rate at which we are pumping water out from this well. Okay, H1, H2 is given here, and this radial distance is given to this well and to this well. Okay, so the during pumping at a constant rate, the final the head difference at this well is H1, at this well is H2. Okay, so what do we have to calculate? We have to calculate the permeability of the layer. You simply have this formula for your pumping test that you might have derived in class lectures, where you get K equals Q log to the base 10 R1 over R2 over 2.727 times H, which is the thickness of this aquifer, into H1 minus H2, which is the head at these two wells. So let's calculate K equals, see, 0.303 log to the base 10. R1 is 18.3, R2 is 9.15 over 2.727 into H is 3.05 into H2 is 2.44, H1 is 1.52. Okay, this comes out to be 2. Sorry, my laptop got turned off. So, okay, let's continue. I need to share my screen. Okay, yeah. So, K, uh, Okay. K comes out to be yes 0.01192 meter per minute, which is approximately 0.0199 centimeter per second. Okay, so that's one question on confined aquifers. Let me check. Okay, this is the same question. Okay, I think let's stop for today with these questions. Okay, thank you very much. Yeah, next class, yeah, compaction. Next class we will do compaction. Any question that you want me to cover in this topic? Seepage, flow nets. Okay, thank you very much. You can always email me. I will provide my email address to you. You can always email. I will provide it right now. Right now, right now. So, no issue, no issue. S underscore SYED at IITR dot AC, sorry, at CE dot IITR